In this session, we will see how a code converter can be designed and implemented that converts a 4-bit gray code to 4-bit binary. That is, a 4-bit gray code to 4-bit binary code converter is what we are going to design in this video. So, the input will be definitely the 4-bit gray code, and what you have to convert that is to a 4-bit binary. So how will you convert a gray code to binary? It is done like this as shown in the figure. That is, the first bit of binary will be nothing but the first bit of gray code, and second bit of binary will be the XOR of first bit of binary and the second bit of gray code. Okay, second bit of gray code XORed with the first bit of binary will give you the second bit of binary. And the third bit, okay, that is B2 will be nothing but B3 XOR G3, and your B1 will be B2 XOR your G1. Okay, so this is how you will be converting a gray code to binary. We will see an example here. For example, I'm writing a number, that is, let's see, I'm writing a number as 0, then 1, 1. This is my gray code. This is my gray code. I need to convert that to a binary. So first bit will be the same as the gray code. So it is 1. Then this 1 XO 0 will be your next bit. 1 XO 0 is 1. Then that 1 XOR 1 will be 0. And that 0 XOR 1 will be 1. So this is how you will convert this gray to binary. Okay, so or there is another shortcut method for this. That is, first step in this design procedure is to you have to prepare a truth table. So truth table input will be gray code and the output will be binary. So your gray code, since it is 4 bits, you'll be having 2 raised to 4. 16 combinations of inputs will be there, 0 to 1, 0, 0, 0, 0 to 1, 1, 1, 1. Okay, and as the binary, you have to convert every input into corresponding binary. So there is another shortcut method for this, how to convert this gray to binary. That is, your B4 is nothing but your G4, and B3 is nothing but your G4 XOR G3, because B3 is actually B4 XOR B1. Sorry, B4 XOR G3, isn't it? That is, your B3 is nothing but your B4 XOR your G3. And what is this B4? You know that B4 is G4 itself. So it is G4 XOR G3. So you can write that next bit of B3 will be G4 XOR G3. And so G4 XOR G3 is your B3, and that XOR G2 is B2. So you can say that B2 is nothing but G4 XOR G3 XOR G2, isn't it? G4 XOR G3 is B3. Okay, so B3 XOR G2 means B3 is G4 XOR G3. So that XOR G2. So G4 XOR G3 XOR G2 is your B2. And so B2 is G4 XOR G3 XOR G2. And that XOR G1 gives you a B1. So we can say that B1 is nothing but G4 XOR G3 XOR G2 XOR G1. That is what I have written here. Okay. Clear. So similarly, we will be finding out every output, binary output of every input. So 0, 0, 0, 0. First B4 will be 0. Then B3 will be G4 XOR G3. So 0 XOR 0, that is 0. Next will be 0 XOR 0 XOR 0. That is again 0. And the last B1 will be 0 XOR 0 XOR 0 XOR 0. That is again 0. Okay, that is how you got the result as 0 XOR 0, 0, 0, 0. Similarly, we can find out this 1, 0, 0, 1. So it is actually 1 for the B4, and then 1 XOR 0, it is 1. Then that 1 XOR 0 XOR 0, again 1. 1 XOR 0 XOR 0 XOR 1, it is 0. So it is 1, 1, 1, 0. So this is how you find out the binary equivalent for every input. And once you got the output binary representations, you have to find out what is the expression for B4, B3, B2, and B1 by drawing the corresponding K-maps. So you found out that B4 is nothing but your G4 itself. G4, you can see that what is G4? G4 is nothing but the B4 itself. So you can write that B4 is equal to G4. And B3 also, B3, we can say that sigma M 4, 5, 6, 7, 8, 9, 10, 11. And that is nothing but your B3 is G4 XOR G3. Okay, that is, we have seen that the same case in converting binary to gray code. In binary to gray code, we have seen that G4 is G3 is nothing but your, see, this is your 4, 5, 6, 7, 4, 5, 6, 7, 8, 9, 10, 11. When that is plotted on the K-mat, what we are getting is B4 XOR B3. So similarly, when you plot this on the K-map, what you will get is your G4 XOR G3. Okay, so that is you obtain the result as B3 as G4 XOR G3, and then your B2. B2, you when plot on the K map, what you obtain will be this G4 dash G3 G2 dash G4 dash G3 dash G2 G4 G3 dash G2 dash G4 G3 G2. You have got 4 pairs, and from the first 2 pair you are taking G4 dash outside, so that G3 XOR G2, because when you take G4 outside, it is G3 G2 dash plus G3 dash G2. That is nothing but G3 XOR G2. Similarly, from taking G4 outside from these two groups, what you're getting is G3 dash G2 dash plus G3 G2. That is G3 XOR G2. That is G3 XOR G2 the complement. Okay. Now this is X bar Y plus X Y bar format. That is, it is nothing but G4 XOR G3 XOR G2. Okay. And what is this G4 XOR G3? G4 XOR G3 is B3. So it is B3 XOR G2. So you can write it B2 as B3 XOR G2. Now your B1. B1 in the truth table, you can see that B1 you take is the sigma value 1, 2, then 4, then 7, 8, then 11, 12, so 13 and 14, isn't it? So when plotted that on the K map, what we are getting is you are not able to group it, so you are going to minimize it algebraically. So when minimized algebraically, what you are getting is G4 XOR G3 XOR G2 XOR G1. So you know that G4 XOR G3 is B3 XOR G2, and this B3 XOR G2 is B2. Okay, so B2 XOR G1. So that is the B1 value. Now you are going to implement this B1, B2, B3 and B4 from the G4, G3, G2 and G1 value respectively. So B4 is G4 and this B3 is G4 XOR G3 and B2 is B3 XOR G2 and B1 is B2 XOR G1. So this is the circuit diagram. This is the code converter that converts your gray code to binary. Hope it is clear for you.